Good morning. Welcome back to physics, start of semester 2. Here we go. So starting things off, we're going into chapter 10 on work and energy. In your textbook, it's titled Work, Energy, and Machines. And then there's a second chapter, 11, that gets into the conservation of energy. So the big idea, starting off semester 2, is what is energy? What is work? What is kinetic energy? What is the work energy principle? What is network? And what is mechanical power? And so those are some of the topics we're going to be discussing. So in response to some of your surveys, what I'm going to try to do for you is prepare an equation sheet for the entire chapter, and I'll put that up online for you guys to access. Some of you, I guess one of the most common themes I found reading through your surveys was that you weren't sure which equation to use and when. And so I'll try to help you stay more organized with your equations. So I'll produce one per chapter, and then you can sort of compile those into one master equation sheet if you wish, or keep them separate. Anyways, let's start by taking a look at this slide here. What this slide is showing us is a concept known as work. And so in everyday life, there's different meanings for the word work. You might think well, you're probably really familiar with schoolwork. There's working out, there's me doing work at a job, and then there's the physics definition of work. And so the physics definition, capital W here, work, has to do with a force, capital F, being multiplied over a displacement. And it's very similar to the concept of impulse, which was the force multiplied by a time interval. So instead of looking at the time a force has been acting on an object, we're going to be looking at the distance over which that force is applied. And that's going to do some mechanical work, which is going to basically either move the object or change the object's speed. So there's a second term, cosine of theta here, which is really important if the force isn't directed parallel to the displacement. So sort of like with lever arms, remember how the force had to be perpendicular to the axis of rotation to get a torque. Here the force has to be parallel to the displacement. So as you can see right here, the person is pulling up at an angle. And so what that means is part of that force is going to be pulling up, and part of that force is going to be pulling horizontally. And the component of the force that is in the same direction as the displacement, the horizontal component in this case, is going to be the force that does the physical work. So we have to take the x component of this force and multiply it by our total displacement. That's going to give us the work. So in the SI system, our units of work are going to be something called joules. And it turns out that joule is also the unit of energy. And so work is really just a way to either to gain energy or to lose energy, to impart energy to an object. And as you'll learn, work is the way in which we change the energy of a system. For now, a joule is equal to 1 Newton times a meter. And what that means is, it should come from our previous slide here where we had a force multiplied by a displacement. So that should make a lot of sense. And unlike momentum, we just sort of kept momentum as the mass, kilograms times the velocity in meters per second. Here we actually have a new SI unit for energy, which is the joule. And that's named after a person, actually. As long as this person does not lift or lower the bag of groceries, he is doing no work on it. What does that mean? So this guy, he's holding this grocery bag. He's walking horizontally here. So here's the displacement vector. And certainly the grocery bag has a weight force, mass times gravity, and there's going to be a force that the person is exerting to support that weight. But in this case, we're going to say that the guy is not doing any work, and we can go back into the definition of work. If we took the cosine of theta, in this case, it would be 90 degrees. And so we would that would not contribute any useful work. So, hold on, I have to sneeze. Okay, where was that? So in this case, the guy is not doing any work. This is a really important concept. He's going to get tired. I mean, you know this, but to move it horizontally, there's no work involved. On the molecular level, probably there's work happening as the muscle cells contract, and those muscle cells are going to have a component vertical to or parallel to the weight, and that's probably coming from the guy's biceps looking at this picture. Anyways, though, for now, if the force is perpendicular to the displacement, it does not do any work. That's a key point. So, will he get tired? Yes. Will he do any work? No. He only begins to do work if he begins to move upwards. And I'll get into that a little bit later. So then we're going to be fighting the force of gravity and moving in that dimension. So here's another example of a force that does no work. And that would be the force of gravity on a satellite. If we remember the velocity vector of an object in uniform circular motion is tangent to the circle, well, the force, the gravitational force here, is perpendicular to the displacement at every moment in time, and therefore centripetal forces do not do work. So now you're probably wondering, well, what does work do? Why do we need it? Well, work. The main thing about work is we're going to be changing the energy of a system, and as we'll talk about here, the energy of the system is going to be something called kinetic energy. And so with this centripetal force, we're not really, we're accelerating towards the center, but we're not changing that linear velocity vector at all. So we're not adding any kinetic energy to the moon. So therefore, we're not really doing any work, if that makes sense. So let's talk about kinetic energy and how we find that. Here's an important equation that we're going to need this chapter, which is kinetic energy. This is the energy of motion, which is 1/2 mass times velocity squared. So if an object has mass and it's moving, it's going to have some sort of kinetic energy. So how does this relate to work? Well, basically what we have here is we can have something called net work that is done on an object. So that could be the net force acting on an object. And we know that if a net force is acting, we expect to have an acceleration. And if we have an acceleration, well, then we would definitely expect to have some sort of kinetic energy. And to find net work, really what it is, it's the change in our kinetic energy. So if we have a final kinetic energy here and an initial kinetic energy, that change in kinetic energy is going to be equal to the work that's done on the object. So let's say I had a car that was driving down the road, and like this case down here, the car here initially has some kinetic energy. It has mass, it has velocity. But at position number 2, the car has increased its velocity, and to do that, we had to apply a net force to get it to accelerate. Well, we can take a look at energy and acceleration from a different perspective. We can say, well, the net work that's done here, the force acting over this displacement, so our definition of work, that quantity is going to be what ultimately leads to the change in kinetic energy, which is going to be the net work that's done. And so we would expect to have more energy in position 2 than we had in position 1. And that increase in energy came from some work that was done by the car, or by the gas pedal on the car, I suppose, something like that. Another point I want to make here is that net work can be negative and it also can be positive. And that has to do with the direction of the force involved. If the net work is positive, our kinetic energy is going to be increasing, and like the previous slide, that force was in the same direction as the motion. If the net work is negative, we would expect the car to be slowing down. We're going to be taking energy out of the system. At the end of the day, we'll have less kinetic energy, and that's because the force is opposite the direction of motion. So I want to go through an example with you guys and show you how this is kind of useful and actually a lot easier than some of the stuff you've been doing. What we have here is imagine just a box that has a mass of 50 kilograms, and let's say I'm going to drop that off a cliff that's 100 meters high. And to this point, we've been looking at, okay, how fast is that box going before it hits the ground? We're going to do a kinematic equation, and we're going to figure out the final velocity. Well, if you didn't like kinematics, you're going to find energy is a lot simpler. It's sort of a shortcut, and I like it, and most students like it too, because you'll see why it's a lot simpler. So if our question is, what's the speed here? We can use the idea of net work and say that the force of gravity is going to be the force, so mass times gravity, multiplied by the displacement, which is 100 meters down. And so the force is in the same direction as the displacement, so we don't have to worry about the cosine of the angle. And so the net work here to accelerate the box is going to be 49,000 joules. So how does that help us find the velocity of the box? Well, if we remember the net work energy principle, the net work equals the change in kinetic energy. So if this is my net work, 49,000 joules, I can set that equal to the kinetic energy equation and solve for the velocity at the bottom of the drop. And so all you have to do is multiply by 2 and divide by mass, square root it, and you have the final velocity of 44 meters per second. Now, if you want, go back and try that same problem with kinematic equation, and you'll see that you get the same answer. And you're probably wondering, well, I thought mass didn't matter for acceleration due to gravity, and it doesn't. I could actually simplify this equation. When I found net work, I multiplied mass times gravity here to get 49,000 joules after I multiplied by 100. But you do have mass on both sides of this equation, so this falls in line with our idea that all objects are still going to accelerate at 9.8 meters per second squared near the surface of the Earth. All right, well, that's a good intro of work and energy. We'll be talking more about conservation of energy and then gravitational potential energy next week. Bye.